So here we've got the second day of this graph sketching stuff, and I told you in the last video that on this video we were going to be focusing on the rational equations, which you can see from the three graphs that we've got here. We're actually only going to do one of them, so it should be a decently short video. I figure if you've got the steps down to graph one of them, you could probably graph just about any of them. It's really just the calculus and the derivative parts that change, but the step-by-step process is exactly the same no matter what the function. So for the non-polynomial, which we'll be focusing on the rational functions, we need to worry about asymptotic behavior. I'm sure you can tell from the word asymptotic, it means asymptotes. And so we need to worry about what asymptotes we're going to end up with. Are we going to have vertical asymptotes? Are we going to have horizontal asymptotes? So for vertical asymptotes, we've got a little detail that we're going to write here, horizontal asymptotes here. I just want to squeeze in one note about what the asymptotic behavior means for horizontal asymptote. So remember, horizontal asymptotes, we've used them in pre-calc. You may have even seen them in like late algebra, but we really defined what they actually mean once we got to calculus. And a horizontal asymptote, what it really truly means is the limit at x equals plus or minus infinity. The limit of the function, like what value does the function approach as x gets infinitely larger or infinitely more negative. And that's what we get for the actual definition of a horizontal asymptote, so we'll be able to check what those limits are, and then we can see if our graph has any horizontal asymptotes. Finding a vertical asymptote is kind of the opposite, actually. So we gave a definition back in the day when we were doing limits. We said that x equals c, so that would be a vertical line, is a vertical asymptote if f of x has an infinite limit. As x approaches c. And what that means that as I get closer and closer to this value of c, like say as x approaches -2, my graph is approaching positive or negative infinity. That's an infinite limit. That would mean that I have a vertical asymptote at that point. Okay, and then we'll also need to check the behavior around the vertical asymptotes, meaning as I come in from the left, am I going to positive infinity or negative infinity? As I come in from the right, am I going to positive infinity or negative infinity? That obviously makes a huge difference with the way your graph looks, so that's very important. So remember, our rules for horizontal asymptotes has to do with the degree of the numerator versus the degree of the denominator. So I'm going to do some kind of shorthand here. Let's say that the degree of the numerator, we'll denote that by n, is greater than the degree of the denominator. So say you have like an x cubed in the numerator and you have just an x in the denominator. If that's the case, then you don't have a horizontal asymptote at all. There's nothing that our graph is approaching as x approaches positive or negative infinity. So if this is the case, we have no horizontal asymptote at all. You may have a slant asymptote, but like we said at the beginning of the year, that is only something that you guys will ever do in pre-calc. Next, if the degrees are equal, if the degree of the numerator is equal to the degree of the denominator, this is usually the one that you guys have down pat. If this is the case, you take the ratio of the leading coefficients. So y equals, because your horizontal asymptote will be a y equals line, y equals the ratio of the leading coefficients. And then finally, if the degree of the numerator is less than the degree of the denominator, there's not really too much thought you have to put into this. It's just always 0. Okay, so those three rules should not be new at all. Those should definitely be a review. This problem right here we are not going to do. We're going to do the one on the next page. But first, I want you to flip back to this page right here, the first page of this set of notes. We learned all the shapes up here. I want you to focus on this bottom part. It says you should end up using all of the following details, so make sure, because only once in the notes did I actually spell out every little detail that we needed. I'm only going to do that once, but you can kind of use it for reference as you're going back and doing notes. But that's a list that you should have. Those are all of the features you should have if they're available to you. All right, so when we are looking at something, a rational function, like, we're going to skip back a couple pages here. We're skipping over this one, and we're going to go on to the back of that page. So make sure that we are all looking at the same function. We are looking for y equals x over x squared minus 9. Okay, so we're going to start with our transition point sign chart, meaning we need the first derivative and its critical points, and then we need the second derivative and its possible inflection points. Then we can set up a transition point sign chart, and we can find the basic shapes of the graph. So that beginning part is still exactly the same. We just have to bring in the asymptote factor since we're talking about a rational function here. So start with y prime. And of course, we're going to get a nice quotient rule here, so a little practice for you guys that deny that the quotient rule exists. We've got low, which is x squared minus 9, d high, which is the derivative of x, that's just 1, minus high, d low, the derivative of x squared minus 9 is a 2x, and then all of that over low, low. Okay, so that is our first derivative, or a very, introductory version of it anyways. So here we've got just an x squared minus 9, and then minus 2x squared. Okay, so I have x squared minus 2x squared, so that gives me a negative x squared, and then the only other thing I have is a minus 9. And here's my denominator. Okay, so for my critical points, remember critical points are anywhere where the first derivative is equal to 0 or is undefined. I told you in the last section when we were doing this, start with the ones that are undefined because they're usually pretty easy to spot. So critical points, x equals, if we look at the denominator definitely can be equal to 0. It would be equal to 0 when x is positive 3 or when x is negative 3. So far we've got plus or minus 3. And then to find out when the derivative would be equal to 0, we set the numerator equal to 0. Well, the only time that the numerator would be equal to 0 is if x squared were a negative 9, because then it would be a negative 9 minus 9. That would come out to be 0. X squared is never ever going to be a negative 9. That would be imaginary answers, and of course while we have imaginary answers, they don't show up anywhere in our graph, so we don't bother to name them as critical points. So just plus or minus 3, and that's just two places where my denominator is 0, which means my derivative does not exist. Okay, so next we are going to take this derivative, take the derivative again. So y double prime. So we start with low, which is this function right here, and then times d high, is the derivative of the numerator, which is a negative 2x, minus high, d low. Now don't forget, for d low we are going to need a chain rule. So chain rule says that the 2 comes out front, we leave the nested function in place. When the 2 comes out front, the power technically drops down to a 1, but we don't need to write that here. We just multiply by the correction factor, which is the derivative of the inside function here. Derivative of x squared minus 9 is a 2x. Okay, so that's the numerator. And then low, low, we now have this quantity to the 4th power, because it's x squared minus 9 squared squared. So we raise that to the 4th. Okay, so lots of cleanup, lots of algebra that we can do here. A couple things, we've got like a 2x. So this is one big term right here, and this is one, even bigger term. So one thing that I would like us to do first, notice we are subtracting and then we're multiplying by this negative quantity. We can help ourselves out a little bit by changing these signs. That'll make things a little bit cleaner, a little bit simpler. So notice that this big term that I underlined and this big term that I underlined, they both have an x squared minus 9, and they both have a 2x. So in my algebra work, I am going to factor those out. So I'm going to factor out a 2x. I'm going to factor out one copy of x squared minus 9. And then the way that factoring out works, you have a big set of parentheses where you write all your leftovers. Okay, so let's do that. So this right here, once I factor out a 2x, I have a negative 1 left. Once I factor out an x squared minus 9, I have another copy left. So negative 1 times another copy of this is a negative x squared plus 9. That's what I have left from this piece right here. This piece, I factored out the 2x, I factored out the x squared minus 9. I still have 2 times the quantity x squared plus 9. So 2x squared plus 18. Okay, so those are all the leftovers. I will clean those up one more time in just a moment. Then I have x squared minus 9 to the 4th. So we've got 3 factors here. This factor, and this gigantic factor. We can take out a copy of this. So cancel out your single copy here. We will be left with 3 copies down in the denominator. And then finally, we are going to clean up this piece right here. So we have a 2x, and then this piece I just combine up my like terms, and I have an x squared plus 27. Okay, and that is all over x squared minus 9 to the third. So it ended up not being all that messy. So when we want to find our potential inflection points, remember we call them potential because we haven't checked a sign chart yet. We don't know if we actually change sign at those points. Our potential inflection points happen whenever the second derivative is undefined or is equal to 0. So the second derivative is undefined at those very same values, plus or minus 3, and it's equal to 0 only when x equals 0. X squared plus 27 is never going to be equal to 0 because x squared would have to be a negative 27, and again, that would be imaginary answers. We're not going to have those here. So with all of these points, we've got 2 critical points, 3 potential inflection points. We're going to set up our double sign chart. So big sign chart for y prime, big sign chart for y double prime. So really we only have 3 transition points because these points and these points are the same. So we've got 0, negative 3, positive 3. All right, and then keep in mind that the first derivative is definitely not going to change at 0, so we really only have 3 chunks on the graph here that we need to plug in for y prime. So for y prime, we're going to take turns plugging in some sample values. So here is our first derivative. One thing to point out is that the denominator will always be positive, so we really only have to worry about the sign of the numerator. Whatever I plug in here, I square it, so I know it's going to come out positive. So just worry about the sign of the numerator. So say I plug in like a negative 10. I would have negative 100 minus 9. That is definitely negative. And then I could plug in something like, I could plug in 0 actually, because remember there's no sign change that's going to happen at 0 because 0 is not a critical point. So I could plug in anything in this range right here. So I could plug in 0. I have negative 0 minus 9. That is also negative. And then something bigger than 3, again I could go with something like 10. Negative 100 minus 9. One thing we could have noticed from the beginning is that this quantity will always be negative as well. No matter what I square, a negative x squared will always be negative, and when I subtract 9, it will always come out to be even more negative. So this numerator is always negative, this denominator is always positive. That means no matter what I plug in here, this thing is going to be negative, which means my graph is always decreasing. I could change concavity, I could have some asymptotes, but it's increasing no matter what. Okay, so now let's look at this function right here. This function right here, I can plug in some sample values. I do have to plug in a different value for each one of these. So say I plug in something like a negative 10. This will be negative. This will be positive. This will be positive. So I have a negative times a positive over a positive, and that comes out negative. Say I plug in something like a negative 1. This will be negative. This will be positive. This will be negative, because this would be a 1 minus 9 cubed. When you cube something, it does retain its sign. So negative times a positive over a negative, that comes out positive. Positive 1 or positive 2, this will be positive, this is always positive, and this will again be negative, because the x squared is smaller than 9. When I cube it, it comes out negative. So this is negative, and then something as big as I want, like 10. Positive, positive, positive. Okay, so that is my sign chart for y double prime. That means that my original graph is concave down, concave up, concave down, concave up. So even though I'm always decreasing, I do have a change in concavity. Okay, so let's go back to this list that we've got and see if there's anything else that we still need. So intervals on which a function is increasing or decreasing. Got it, always decreasing. Concave up or concave down, we've talked about those. Local extrema and their y values. We don't have any local extrema, so we don't need to find their y values. Inflection points and their y values. So that'll be next. So inflection points and their y values. So let's start with that. So negative 3 is supposedly an inflection point. So let's plug in negative 3. So when I plug negative 3 into my original function, I get negative 3 over 0. Okay, so that means it's undefined. So what does that tell us? That tells us that negative 3 is a vertical asymptote. Okay, so we were trying to find our inflection point, but we actually ended up finding a vertical asymptote. Okay, so now let's try to plug in the 0. And I plug in 0 into my original function. I get 0 over negative 9, but that's still just 0. Okay, so then I have an inflection point at 0, 0. So I'm going to change inflection there. I'm going to change from concave up to concave down. And then this also treats as my y-intercept. So I just found my y-intercept also. And then when I try to plug in 3, I get 3 over 0. So that actually turns out to be another vertical asymptote. Okay, so I attempted to find my inflection points. I found one of them, and then I found 2 vertical asymptotes. So back to our list. Got this, number 4, asymptotes. Okay, so now we're worrying about that. Okay, so we found our 2 vertical asymptotes, and we found our vertical asymptotes basically by setting the denominator equal to 0. We want to check the signs around it to see if my function is going to be increasing or decreasing or what. And then I've got 1 horizontal asymptote. If I go back to the original function, the degree of the numerator is smaller than the degree of the denominator, so that means I have a horizontal asymptote of 0. Okay, so let's set up all of this information into one big graph. Okay, so at 1, 2, 3, I have a vertical asymptote. At negative 1, negative 2, negative 3, I've got another vertical asymptote. And then y equals 0 is a horizontal asymptote. Okay, now what else do I have? I've got an inflection point at 0, 0, and that is my y-intercept. If we look here, the only y-intercept I have is 0. The only x-intercept I have is 0, because if I set y equal to 0, I just get 0. So this is the only point where my graph crosses through the x-axis. Now remember your pre-calc rules where you were told that an asymptote was a rule that you could never cross, or a line that you could never cross? It's not necessarily true. It was given to us because that was the best definition we had at the time, but now we have these calculus definitions. All right, so a horizontal asymptote is just something that our line gets closer and closer to as x goes out towards positive and negative infinity. We are nowhere near positive or negative infinity here. Okay, so here's what we are going to plug in. We've got this region over here. That is the region to the left of negative 3. My function is decreasing and concave down. Picture that shape. In order to be decreasing and concave down, it looks like this. Now picture where that shape can go. I either have, it could be this scoop right here, just based on my asymptotes, or it could be this scoop right here. Well, based on the shape, we know it's got to be this scoop down here. And you could always test that out by plugging in a sample value over here. Say I plugged in like negative 10. If I plugged in negative 10, I would get a negative y value. So I know I'm supposed to be down below the x-axis. So let's extend this a little bit so I can get a good shape. So go along my horizontal asymptote, head down here towards my vertical asymptote. That's the first piece of my graph. It is decreasing and it is concave down. Then I have vertical asymptotes. There's no connection between this piece and the next piece. Next, I jump for the piece between negative 3 and 0. My graph is decreasing and concave up. Again, the only way to be decreasing and concave up would be in this top half. Decreasing and concave up would look like this. So I go like this, concave up, come through, hit this point, and then at this point, I know it's an inflection point. So I'm going to continue decreasing, but now I'm going to be concave down. So switch to being concave down, and then go right along that other vertical asymptote. So there's my piece there. My final piece is decreasing and concave up, so it's going to be another piece that looks like this. So it's got to be in this top half right here. Okay, so that is my graph. We also could have figured out exactly where these pieces were by plugging in sample values into the original function, because the original function would tell you if the y value should be positive or negative, and that can tell you if it would go above the x-axis or below the x-axis. We could have done that for all 4 of these pieces, but we just kind of use the shape and a little bit of common sense to know if it's going to be in the top half or the bottom half. All right, so that's it.